All right, strap in everyone, because today we are diving deep, deep into something so mind-bending.
Oh, yeah.
It's super solid light.
It's incredible.
Light acting like a solid.
I know.
I mean, how is that even possible?
It really challenges how we think about matter, doesn't it? You have this idea of a super solid.
Right.
It has this rigid structure of, like, ice, but it can also flow without any resistance.
Right, like a superfluid.
Exactly, yeah.
So it's both at the same time.
Yeah, and it's a concept that's just boggled physicists for, I don't know, decades.
Right. And for the longest time, it was just theoretical, right?
Yeah, just theoretical.
You could only create it with these ultra-cold atoms
right.
in a lab.
Yeah.
Not exactly something you encounter every day.
Exactly.
But the research we're going to be looking at today, these scientists, they actually managed to create a super solid light using light.
It's amazing, isn't it?
That's what's so crazy about this.
Yeah, and not the typical way either.
Yeah, it's completely...
Not those ultra-cold atoms, like you said, a whole new approach.
So we have some fascinating articles here detailing the experiment and how they did it. Let's unpack it a little bit.
Sounds good.
So they start by firing a laser at a specially designed piece of gallium arsenide.
Okay.
Now, this isn't just your run-of-the-mill gallium arsenide.
Oh, right. No. They got clever.
Yeah.
They etched these little tiny ridges onto the surface of the gallium arsenide.
Like an obstacle course.
Yeah, like a microscopic obstacle course for the light.
Okay, I can picture that.
Yeah.
So how do these ridges actually lead to the formation of a supersolid?
Well, here's the thing.
Yeah.
As the laser light interacts with the gallium arsenide, it forms these particles called polaritons.
Polaritons, okay.
And polaritons are really special because they're hybrids.
Hybrids.
They blend the properties of both light and matter.
Okay, so they're kind of in between, right?
Yeah, they're not just light. They're not just matter.
Got it.
They embody this duality.
Okay.
And that's why they can form a supersolid.
Interesting.
See, the ridges on the gallium arsenide force these polaritons to interact in a really specific way.
So they're kind of like corralling them into a specific formation.
That's a great way to put it.
Okay.
And that formation, as you may have guessed, is a super solid structure.
Wow.
So this method of using light and manipulating polaritons is completely different from the old way.
Yeah.
Scientists created supersolids.
Right.
It's a new path to this bizarre state of matter.
So they created it out of light, but how do they actually know for sure that it's a supersolid?
Yeah, the point.
Did they actually, like, test this?
Absolutely. They didn't just assume they had a supersolid on their hands.
Yeah.
They ran a battery of tests
Okay.
to confirm that it had all the hallmarks of a true supersolid. And one of the key things that a supersolid needs to do is it needs to act like a solid and a fluid at the same time.
Oh, wow.
It has to have that rigid structure, but also be able to flow.
So solid and a superfluid.
Yeah, exactly.
At the same time.
Simultaneously. And that's exactly what they saw in this experiment.
Okay.
The structure they created with the light, it had that crystalline order, which is, classic solid behavior. Yeah. But it also flowed without any resistance.
Like a superfluid.
Exactly, like a superfluid, yeah.
So zero resistance?
Yeah.
I mean, are we talking...
It's mind-blowing.
The ultimate frictionless material here.
In essence, yes. I mean, imagine a substance where particles just glide past each other.
Right.
No friction.
Wow.
No energy loss.
That's amazing.
And they actually confirmed this zero viscosity through experiments.
So they saw that the polaritons were just flowing effortlessly.
Exactly.
That's wild.
Yeah.
So, okay, they observed this kind of dual nature, the solid and the superfluid.
Right.
What other tests did they run?
Well, they wanted to be extra sure.
Right.
So they looked at the density of the polaritons and the structure, and instead of just seeing like a uniform blob of polaritons, they found this periodic variation in the density.
Okay.
So there were areas where there were more polaritons and areas where there were less.
Got it.
This density modulation is another sign pointing to it being a supersolid.
Okay, so they have the structure, they have the flow, they have this density pattern.
Yeah.
What else?
Well, to really nail it down, they went even deeper into the quantum world.
Okay.
And they actually measured something called the wave function phase.
Okay, this is where it gets a little complicated for me.
Yeah, I know this is getting pretty deep into quantum mechanics, but basically the wave function phase gives you information about how coherent the superfluid part is.
Right.
And their measurements showed this coherence across the entire structure, which means the whole thing's acting as one unified quantum entity.
Interesting.
Even more evidence for the supersolid nature.
Okay, so we've got the structure, the flow, the variations, and this coherence. Yeah. Anything else?
One more thing that really sealed the deal for them.
Good.
They found evidence for these things called phonon-like excitations.
Phonons. I'm not familiar with that term.
Oh, so think of phonons as like collective vibrations of particles within a material. It's like sound waves, you know, traveling through a solid. Okay. The fact that they found these phonon-like excitations within this light-based structure
is a big deal because it supports the idea that it's really behaving like a solid.
Wow.
Even though it's made of light.
That's so cool.
I know. It's showing properties that we normally associate with solid matter.
So they've created something that challenges like our entire understanding of both light and matter.
It really does. It's amazing work.
And it's not just about creating the supersolid itself, right?
Right.
There are like huge implications for research and potentially even technology.
Absolutely.
That's what we're going to get into.
I'm excited.
In the next part of our deep dive.
Let's do it.
So I'm really interested to hear more about these implications, these potential implications.
Yeah, me too.
We've talked about the fact that they made a supersolid out of light, which, I mean, just that in itself is like mind-boggling.
It's why.
But what does it actually mean, you know, for the future of research and maybe even, you know, technology? Well, for me, what's really exciting is that these light-based supersolids might be the key to understanding supersolid physics better.
Like on a deeper level.
Yeah, exactly.
Why is that? I mean, what makes them easier to study than, you know, the ones that are made with ultra-cold atoms?
Okay, so think about it. Yeah. Light is so much easier to manipulate, to work with, than ultra-cold atoms. I mean, we have lasers, we have lenses, we have detectors, all these tools to probe them with light. And, you know, with ultra-cold atoms, you need these crazy low temperatures and really complex setups. Right. It limits what you can do.
Okay, yeah.
But with light, it's like we have this new window into the world of supersolids.
So it's kind of like an easier, more accessible way to study them. Exactly. So that's obviously huge for the scientific community. Yeah. But I also want to talk about, you know, like the potential for applications beyond just research.
Right.
Could this lead to like new technologies?
Yeah, it's still early.
Yeah.
But the possibilities are really intriguing.
Like what kind of things are we talking about?
Imagine using supersolid light to create super sensitive detectors for things like gravitational waves or even dark matter.
Wow.
I mean, these are things that are really hard to detect. Right. They interact so weakly with normal matter. Right. But a supersolid made of light, it could be what we need to pick up these faint signals because it has these unique quantum properties. Right. You know? So
basically taking advantage of the properties of the supersolid to actually sense these.
Yeah, and not just that. Think about sensors, too. Yeah. I mean, sensors that could pick up tiny changes in temperature or pressure or even magnetic fields with, like, amazing accuracy. I mean, that could have applications in everything. Right. From environmental monitoring to medical diagnostics.
Oh, okay. It's easy to get caught up in these possibilities.
Definitely.
But, you know, I think it's also important to remember we're still in the very early stages of research.
Absolutely. We don't want to get ahead of ourselves.
Right.
There's still a lot to learn. Yeah. There's a lot more research that needs to be done before we see any of this stuff become a reality.
Yeah. Yeah.
But that's what makes it so exciting.
It is.
We're on the verge of a new era in how we understand matter and light.
It really feels like it. Yeah.
Yeah, and who knows what other breakthroughs are waiting for us. Right. It's going to be amazing.
So you've painted a very clear picture, I think, of why this is such a big deal. Yeah. It's not just about making a super solid out of light.
No.
It's about opening up all these new possibilities for research and potentially for technology.
It's really exciting.
And it's all connected, right? Like this discovery is part of a larger story in physics.
It's all part this quest to understand, the fundamental building blocks of the universe,
right,
and the crazy ways that they can arrange themselves.
So we started with, the basic states of matter,
right,
solids, liquids, gases.
Yeah.
Then we discovered plasma.
Yeah.
And then more recently, Bose-Einstein condensates, where the atoms are all acting like one giant superatom.
It's wild.
And now we have supersolids.
I know, right?
It's just adding another layer of complexity.
Yeah, exactly.
To this whole picture.
And each new discovery, it forces us to rethink things. It challenges our assumptions.
Yeah.
And it gives us a deeper glimpse into how the universe actually works.
It's a constant evolution, right?
Exactly.
It's we're always learning.
Yeah, always learning new. And I think it's kind of funny, we always thought of light as this fleeting thing, this intangible thing.
Yeah.
And now we're seeing it behave like a solid object.
It's really, it's kind of humbling, you know?
Yeah, it really is. It makes you realize we still have so much to learn.
Yeah.
I mean, even the things we think we understand can still surprise us.
And this discovery, I mean, not only does it have the potential to lead to these breakthroughs in science, but it also, really highlights the importance of continuing to explore.
Oh, absolutely.
And continuing to question what we think we know.
Yeah, I think we've
covered a lot today.
I know, this has been great. From, the nitty-gritty of the experiment to what it could mean.
I know, it's exciting stuff.
For the future.
I agree.
So just to bring it back to our listener for a second.
Okay.
What would you say are the key takeaways here?
I think the biggest takeaway is that we've seen a total shift in how we think about light and matter.
Okay.
Scientists have figured out how to make light behave like a solid.
Right.
Which was unthinkable before this opens up all these new ways to study supersolid physics. And, it hints at maybe some revolutionary technologies down the road.
Right.
But I think most importantly, it reminds us that the universe is full of mysteries.
Oh, absolutely.
And we're just starting to unravel them.
And it really sparks that sense of wonder,
For sure.
Okay, so before we move on, I just want to leave our listener with a little something to ponder.
Okay, I like it.
We talked about the potential application.
But imagine we could take this idea even further.
Okay.
If we can manipulate light to make a super solid, what other impossible states of matter might be out there?
That's a good question.
What other boundaries of physics can we push?
Yeah, what else can we do?
It's a pretty mind-blowing thought.
It is. Yeah, it's a reminder that we're only scratching the surface of what's possible.
Exactly.
And who knows? Yeah. Maybe our listener will be the one to make the next big discovery.
That would be awesome.
I know, right?
So I love that thought.
Yeah, it's a great thing to think about.
Okay, so I think we've given our listener plenty to think about regarding, super solid light and the future of it all.
Definitely.
But before we wrap up, I'm curious to hear your perspective on how this research connects to the broader landscape of physics.
Yeah.
It's like we've been trying to figure out what matter is really all about for forever.
Yeah, for centuries, right.
Yeah.
Trying to understand the fundamental nature of it.
And we keep finding these new states of matter.
It's amazing.
We started with the basics. Solid, liquid, gas.
Solids, liquids, gases. Right.
Then there's plasma.
Yep.
And more recently, Bose-Einstein condensates.
Yeah, those are mind-blowing.
Which is a whole other thing.
A whole other deep dive.
Right.
Yeah.
And now we have supersolids.
Right. It's like we keep peeling back layers of an onion or something.
Yeah, and with each discovery, we're kind of refining our models.
Exactly.
Challenging what we thought we knew.
Totally, yeah.
And getting a better understanding of the underlying principles.
Yeah, the principles that govern the universe.
Like this super solid light finding.
Right.
It's not just some random thing. It's part of this larger...
part of this journey, the scientific journey that we're all on.
Right. It's amazing to think that, we used to think of light as this almost mystical thing.
This ephemeral thing, right.
Yeah.
Like you were saying.
And now we're seeing it act
in
these ways that just challenge everything we thought.
Yeah, it really does.
Could be new.
It makes you realize that we really don't know.
Right.
everything, you know?
Yeah.
Like, even the things we think we understand can still surprise us.
And it really highlights,
Yeah.
you know, the importance of
Absolutely.
constantly exploring.
Yeah, keep exploring.
And questioning what we think we know.
Exactly.
I think we've covered a lot of ground today.
Yeah, it's been a great deep dive, I think.
You know, from the details of the experiment all the way to, like, what this could mean.
The implications,
for the future.
It's exciting stuff.
I think we've given our listeners
I hope so.
a lot to think about.
I think they have a lot to chew on, yeah.
Yeah, for sure.
So to wrap things up, I just want to say, you know, to everyone listening, stay curious.
Yes.
Don't be afraid to dive into the complexities of science.
I love that.
It's a world full of wonder.
It really is.
It's full of discoveries waiting to be made, questions waiting to be answered.
And this research that we talked about today, it's proof of that.
It really is. It's a testament to the power of curiosity and exploration.
Absolutely.
There's always more to learn. There's always more to explore.
Yeah.
There's always more to understand.
Couldn't have said it better myself.
I tried my best.
Well, to our listeners, thank you so much for joining us on this incredible journey.
Yeah, thanks for listening, everyone.
You know, we hope you've come away with a new appreciation for the wonders of super solid light. And maybe a little bit of that curiosity to learn even more.
Definitely.
So until next time, keep questioning.
Keep exploring.
Keep exploring. And keep that thirst for knowledge alive.
Cheers to that.